Hello and welcome to today's lesson looking at the advanced aspects of the national grid, which is found in the GCSE Combined Science and GCSE Separate Science courses for physics found in the electricity module. So in today's lesson we're going to try and understand and justify the layout of the national grid. So we're going to understand what we mean by the national grid, detail the layout of the national grid, and justify the layout of the national grid to allow electrical energy to be transferred efficiently, which falls into the following part of the AQA Combined Science and AQA Separate Science course for physics in the electricity module. So we're focusing on the topic 4.2.43, the national grid. Now the national grid, like we've talked about previously, is a network of transformers and transmission cables that carries electrical power around the country. Now electrical power is generated at the power stations and distributed around the UK through a vast circuit of electrical transmission cables. Now before we had the national grid, each town had its own power station and the setups had different potential differences in each town. That meant that if a neighbouring town had a high demand for electricity and other towns had a surplus of electricity, those towns couldn't supply the electricity to the town in need because of the differences in potential difference. So that meant that each city or region had to have its own power supply and were independent of each other. Now some countries still adopt this way of transferring electrical power. So for example, America has 4 different electrical grids due to its vast size. So certainly the different grids can't then link into each other to transfer electrical power between the different grids. Now the national grid has not always been about in the United Kingdom. It's an invention that's only been around for about 80 years, since 1926. So basically in 1901, Charles Mears opened the first major UK power station, which was on the River Tyne, a hydroelectric power station, which is ironic considering many people thought the first types of electrical power stations were coal, oil and gas. Then the first integrated power system developed by Mears in the northeast of England, which was the largest in Europe, which used an alternating current system, was developed in 1912. But the rest of the UK still used a patchwork of small supplying networks. And in 1925, the UK government asked people to look into the inefficient electrical supply around the UK, and this resulted into the formation of the Central Electricity Board. Then in 1933, the Central Electricity Board set up the UK's first nationwide alternating current grid running at 132,000 kilovolts and 50 hertz. This was then upgraded to 275,000 volts in 1949. Then in 1965, the grid was further upgraded by adding some 400,000 volt lines, which we still have in today. Now, looking at a report on the national grid, you'll notice that there's little electrical energy dissipated in the national grid. So you'll notice that we have a maximum demand of 63 gigawatts and a capacity of 80 gigawatts. However, we tend to have only losses around about 1 gigawatt. Now, on average, approximately 11 gigawatts are produced in the north of the UK and transferred throughout the grid to be used in the south. Now, that's expected to be about 12 gigawatts by this point. Now, as a result, this shows us that little electrical energy is dissipated in the national grid. That's due to transmission in low current and high potential difference and using materials with a low resistance in our national grid. Now, most of the power stations are found in the north of the UK, but most of the demand for electricity is in the south of the UK, around the London, southeast area, but that's only possible to transfer electrical energy from around different parts of the UK using a national grid. Now, some parts of the country are not connected to the national grid. That's because they're too remote to make it economically viable to connect to the grid. So these places have to have their own power supply. This is the reason why many sparsely populated or unevenly distributed countries don't have a power grid. It's because it's not economically viable to connect all the remote regions to the grid. So for example, many Scottish islands are not connected to the national grid, as it will be very expensive to connect the island to the grid, and there'll be very few customers taking advantage of the electricity supplied. So this will make the project unprofitable or not economically viable. So many of these islands have their own small power stations or their own small power grids which supply the electricity needs of the island. Now, on extremely small islands, individual homes have their own private generators to produce electricity. Now, in fact, this can also lead to an advantage because many areas which have their own power supply can sell their electricity that they generate in these areas to the grid, so they in fact act like mini power stations. Now, in 2020, lots of farmers tend to make more money selling electricity back to the national grid than from agriculture, which is where the phrase wind farm comes from. So lots of farmers these days have wind turbines on their farmland that then get connected to the national grid and it acts as a mini power station. Now, this is the case in many windy areas of the world. So in Denmark and in the plains of Texas, there are many small-scale developments of wind turbines on farms which are connected to the appropriate grids. Now, it's cost-effective for the United Kingdom to have a national grid, as there's a great spread of population throughout the country, and the national grid makes it cheaper to transfer electricity around the country and from areas where the electricity can be generated. So because the UK has a spread of people throughout the country, it makes it economically viable, so it makes it profitable to construct a national grid to transfer electricity all around the country. Again, another country which can do this is France, because France has a spread of people throughout the country. It makes it economically viable to construct a national grid to transfer electricity around the country. So here, for example, is the French national grid, similar to the UK national grid, except it's just obviously in France. Now, in many developing countries, the population is not spread out throughout the country. This means it's not economically viable to have a national grid. It's only viable to have the transmission lines between the areas of high population, not the entire country. So, for example, in Kenya, there are very few people in the north of the country and in the east of the country. So it doesn't make it economically viable to construct a national grid, as there's very few people in those northern and eastern areas. So it's not because Kenya doesn't have the money or can't afford to construct a national grid, it's just not very cost effective to do so. Now, linking into the national grid, you'll notice in the United Kingdom that we have overhead transmission cables which carries the electrical energy around the country. But there's a big debate regarding this. Should we construct our national grid with overhead cables or underground cables? And why do we have overhead electrical cables in many instances when many other cables such as broadband internet and Virgin TV are placed underground? Well, there are many advantages to building a national grid with transmission cables overhead. They're cheap to install. There's little disturbance to land and habitats when we install them. They don't tend to influence the existing areas around them. It allows electrical power to be transmitted over water very easily. So for a country like the United Kingdom, which has lots of lakes and rivers and streams, that's very important. The cables are easy to access if there's a fault with the cables. It's very easy to go, as you can see in the picture, to actually fix any issues in the national grid when the transmission cables are overhead. But there are also many advantages to building a national grid with transmission cables underground. They're out of sight. The cables are not a risk to low-flying aircraft. The cables are unlikely to be damaged by weather, so less maintenance is needed, making the cables more reliable, and there's less risk of electrical shock to humans, and the electrical field produced by the cables is less likely to affect modern technology as it's buried underground. Now, in the national grid currently, we tend to construct the cables overhead. However, insulators used on electrical pylons need to be very effective, or else electricity would short circuit to the ground, and in the winter, ice on the cables can cause them to snap. Now, teams of electrical engineers are always on standby to deal with these sudden emergencies. Now, as well as that, throughout the day, electrical uses change in the country. This is what we call the demand for electricity. Now, the national grid has to be used to meet this demand. Now, the demand increases when people get up in the morning, come home from school or work, and when it starts to get dark or cold inside. Any instance where people turn on electrical appliances. So another example could be popular events like a sporting final, like the Champions League final or the FA Cup final being shown on TV, or a popular TV show can also cause a peak in demand. Now, the peak in demand is the maximum value of electrical power required in a certain time. That's the highest part of the graph, whilst the base load demand is the minimum level of electrical power on an electrical grid over a span of time. So you can observe that because it's the lowest point of the graph. Now, when the demand for electricity is greater than the base load, the national grid reacts by providing additional electricity. Now, many power stations in the national grid run at below their maximum power output, what we call in the intermediate stage, so the spare capacity. Now, why do they do this? Well, that's in case there's a high demand, there's a sudden peak, okay, for electrical power, such as lots of people turn their TVs on all at once, or lots of people turn their lights on all at once. Or you can also have these spare capacity in case a power station unexpectedly shuts down in the national grid. So the other power stations have to then rise their output, so there's not going to be a shortfall for people in the intermediate time. Now, lots of smaller power stations which have a short startup time are used to meet any sharp increase in demand. Now, this tends to be hydroelectric in gas power stations because they can, from when they're turned on, they can produce electrical power very, very quickly. So if there's a sharp uptake in demand, they can meet it easily. Now, power stations which have a long startup time and are reliable are used to meet the base load demand, so they don't have to ever be turned off, because if they're turned off, it takes them a long time again to start producing electrical power, so there's no point in turning them off. Now, nuclear power stations and coal-fired power stations tend to be used to provide the base load demand in the United Kingdom. So let's just look at what we've learned about the national grid in the past couple of lessons. The national grid is a system of cables and transformers linking power stations to consumers. Electrical power is transferred from power stations to consumers using the national grid. Step-up transformers are used to increase the potential difference from the power station to the transmission cables. Then step-down transformers are used to decrease to a much lower value the potential difference for domestic use. And you should be able to explain why the national grid is an efficient way to transfer energy. So if we've learned in today's lesson, we understand what the national grid is, we can detail the layout of the national grid, and we can justify why we have the national grid to allow electrical energy to be transferred efficiently around this country. I hope you've enjoyed today's lesson, looking at more advanced aspects of the national grid and how it links into electrical production and distribution in general, and have a lovely day.